As mentioned in the previous lecture, a feedback amplifier has two parts, namely amplifier circuit and feedback network. The feedback network usually consists of resistors and it returns a fraction of the output energy back to the input. As we have seen that out of the four different feedback connections, namely voltage series feedback, voltage shunt feedback, current series feedback, current shunt feedback, the voltage series feedback is the most commonly used one because of its increased input impedance and decreased output impedance, which is capable of achieving an impedance matching in the case of a multi-stage amplifier. Now consider a voltage series feedback as shown in this diagram. Some typical numerical values have been assumed to make the treatment more illustrative. The output of the amplifier is 10 volt. The fraction MV of this output voltage is fed back to the input. That means the output voltage of 100 millivolt is fed back to the input signal. So here we are feedbacking 100 millivolt from a 10 volt output. That means this MV, the fraction is 1%. 1% of the output voltage is fed back to the input. Here the input signal is having a voltage of 101 millivolt. As the feedback voltage is connected in series with the signal voltage and the feedback is negative, so the actual input voltage which appears in the amplifier input is the 1 millivolt. That is, the signal voltage is actually 101 millivolt and we are providing a 100 millivolt negative feedback, so the actual input voltage which appears on the input of the amplifier is 1 millivolt. Now the gain of the amplifier without feedback is actually the ratio of the output voltage to the actual input voltage of the amplifier. That is, the actual output voltage is 10 volt and the actual input voltage of the amplifier circuit is 1 millivolt. So this will be equal to 10,000. So the gain of the amplifier without feedback is 10,000. Now if we calculate the gain of the amplifier with feedback, which is the ratio of the output voltage to the signal voltage, the output voltage is 10 volt divided by the signal voltage is 101 millivolt, so it comes around 100. So here the fraction of the output voltage fed back, that is the feedback fraction, which is called the feedback fraction, is MV is equal to the feedback output, that is 100 millivolt, the feedback voltage, divided by the output voltage, that is 10 volt, which is equal to 0.01, that is 1%. So these are the cases with a voltage series feedback, and you can see that the voltage gain of the amplifier is reduced when we are using a negative feedback. So now following points may be noted. When the negative voltage feedback is applied, the gain of the amplifier is reduced. In this one, in the negative voltage feedback, remember that the voltage gain is decreased and the current gain remains unaffected. So the power gain will decrease because the power gain is the product of the voltage gain and current gain. However, the reduced power gain is compensated by the increased bandwidth. So this negative voltage feedback is commonly employed due to this reason. So in the previous example, we have seen that the gain of the amplifier without feedback is 10,000 and gain of the amplifier with feedback is 100. So we can say that in a negative voltage feedback circuit, the gain of the amplifier is reduced. Another point is that when negative voltage feedback is employed, the voltage actually applied to the amplifier is extremely small. In the example which we have discussed here, you can see that even though the signal voltage is 101 millivolt, the actual input voltage which appearing across the input terminal of the amplifier is only 1 millivolt. So we can say that when negative voltage feedback is employed, the voltage actually applied to the amplifier is extremely small. And also you can see that another thing is that the feedback fraction MV is always have a value between 0 and 1, because 0 means no feedback is applied, 1 means the entire output has been fed back to the input. So actual feedback will be between these two things, that is either there is no feedback or the total output voltage is fed back. So the feedback fraction will lie between 0 and 1. Another important thing which we have to note here is that if we consider a circuit with feedback, this amplifier circuit and the feedback network forms a loop here. So the gain of the amplifier with feedback is called closed loop gain. It is usually represented by AVF. Some others may use the letter AV prime to represent the closed loop gain. The closed loop gain is the gain of an amplifier with a feedback, and sometimes it is represented by AF, the gain with a feedback. This AVF actually represents the voltage gain of the amplifier with feedback. Some others will use AV prime instead of it, some others will use AF. So conventionally you can use any symbol. Also, when the feedback network is removed from the circuit, then the loop is opened. Then we can call the gain without feedback as open loop gain. It is usually represented by AV or A. Simply the letter A represents the open loop gain, or AV represents the open loop voltage gain. So the open loop voltage gain means the gain of an amplifier without feedback circuit. So these are the important points which we have to keep in mind when discussing about a feedback circuit or a feedback amplifier. Now we have to obtain an expression for the gain of a negative feedback amplifier. For that, consider an amplifier circuit shown here. Here we are having an amplifier circuit with the gain AV. And a feedback circuit which feedbacks a fraction MV of the output voltage back to the input. Consider V0 be the output voltage of the amplifier, then MV V0 will be the feedback voltage fed back to the input by the feedback circuit. Let Vs represents the signal voltage. Then since it is a negative feedback, the actual input voltage which appearing in the input of the amplifier circuit will be Vs minus MV into V0. That is the signal voltage minus the feedback voltage. Now we can make these points here. The gain of the amplifier without feedback, that is AV, or we can call it as the open loop gain, is given by the ratio of the output voltage to the actual input voltage of the amplifier. That is, here the output voltage is V0 divided by the actual input voltage of the amplifier. Input voltage to the amplifier is Vs minus MV into V0. And the gain of the amplifier with feedback, that is called the closed loop gain. Here I am using the notation AVF to represent the closed loop gain, which is the ratio of the output voltage to the signal voltage. Here the output voltage is V0 divided by the signal voltage is Vs. Now consider this equation, that is, if we modify the first equation, the AV is equal to V0 divided by Vs minus MV into V0. That can be written as, if you cross multiply it, it will be V0 equal to AV into Vs minus MV into V0, which is equal to AV into Vs minus AV MV into V0. If we take this term to the LHS, then we are having V0 plus MV AV into V0 is equal to AV into Vs, or take V0 as common factor, so it is 1 plus mv into AV, which is equal to AV into Vs, or V0 by Vs is equal to AV divided by 1 plus mv into AV. But according to this equation, the equation number 2, V0 by Vs is the closed loop gain AVF. So AVF is equal to AV divided by 1 plus mVAV. That is the closed loop gain. AVF is given in terms of the open loop gain as AVF is equal to AV divided by 1 plus mVAV. So this equation tells that when negative feedback is applied, the voltage gain is reduced by a factor of 1 plus AV into mV, where AV is called the open loop gain, AVF is called closed loop gain, mV is called the feedback fraction, and mVAV is called feedback factor. That is, mVAV is called feedback factor, and 1 plus mVAV is called feedback sorry 1 plus mVAV is called the loop gain. So mV is the feedback fraction, mVAV is the feedback factor, and 1 plus mVAV is the loop gain, and AVF is the closed loop gain, and AV is the open loop gain. So this is a very important expression in the case of a negative feedback amplifier. Thank you.